Hello, good afternoon, everybody. So, Asakami has the same title in the agenda, so I was thinking that maybe I should choose a title for my presentation, and I decided to choose Exploring Extreme Sea Level Events. First of all, I would like to thank Phil and rest of PSMSO people for the invitation to be here talking about extreme sea level events. I wrote this title, Exploring Extreme Sea Level Events, and then I thought, okay, this is a quite general title, so maybe I can choose a more specific title for the presentation, and I wrote Exploring a Climate Variability of Extreme Sea Level Events by Using Non-Stationary Extreme Statistical Models. And then I saw the title and I thought, okay, it's so long, so please take care only about these keywords. This talk is about climate, and climate can be understood in a raw way as the mean weather conditions, and it is well accepted by the climatology community that we can obtain some kind of values that we name climatologies from 30-year record time periods. Okay, and this talk is also about extremes, or what Phil's named unusual extremes. So this talk is about extreme sea level events that maybe has not occurred in a time period of 30 years. I like also the word of non-stationarity, because any work, it could be meteorological, climatological, engineer, whatever work that we are going to do, we are going to work with any geophysical variable is involved in the climate Earth system. Therefore, we are going to have always a non-stationary behavior, even for the extreme sea level events. Because all these three characteristics, the only way to achieve extreme sea level events is by means of statistics. And there is a specific statistical discipline to study extremes. Its name is extreme value theory. And what the extreme value theory tries to do is to model some values that has a very low occurrence probability. To do that, we used to work with something that we name return levels. That means a value which is associated with a return period, also named recurrence interval. For example, 50 years or 100 years. To do this, we cannot work with high percentile time series. I would like to highlight that this statement that says extreme value theory is maybe the most important statistical discipline for the applied science over the last 50 years. Okay, so here we are. This could be the long-term distribution of a sea level record, but we are going to focus on the extreme distribution. So this could be an extreme distribution. And in fact, we are interested in the red area, that is the upper tail, say, when we have the information about the return levels. Okay? And moreover, we know that the probability of an extreme sea level varies through time. So what we have is not something like this. This could be time. This is a stationary case. What we can have is something like this. If we assume that the extreme sea level values vary through time with a similar behavior than mean sea level rise, we can have a 50-year return level with some behavior like this, a rise and also an acceleration. And if we go to shorter time scales, we can have many more climate variability. For example, this could be winter, summer, interannual variability, long-term trends, etc. Okay? So this is the concept of the non-stationary extreme value model. So now let's go to extreme sea level values. I think one of the most important topics that we should do ongoing research and we should investigate more is about the dominant contribution of each component of an extreme sea level event. And I here choose a triangle to define the main components of an extreme sea level value. They can be mean sea level. Mean sea level has internal and external forcings, but maybe the most interesting forcing is the anthropogenic forcing. Okay. We have also tide. High tides could be a very dominant factor on extreme sea levels, and tide means astronomical forcing, external forcing, and we have also storminess. Storminess is named internal feedbacks, and they can, by means of the pressure and wind atmospheric forcing, they can cause storm surges, or if we go to the coast, we can have also a sea surface elevation due to wave setup. And we need to investigate more about each independent component, but I think it's also very important to understand better the complex relationships between them. And there are many recent papers and works about the understanding how it works relating to extreme sea levels. Here I have shown some examples, but sure you can find many more. Okay, other thing that I would like to remark before show some application is that when we are going to work with, when we are going to develop extreme sea level work, we need to take clear pros and cons of the data source we are going to work. And the data source could be tide gauges, could be satellite, and they could be models. And each of them has sometimes good things, sometimes bad things. We can understand sometimes a spatial distribution, but we are also looking for the longer as possible records when we are trying to understand extreme sea level behavior. Other thing that must be also in our mind is the different time scales that we have when we are working with extreme sea levels, different climate variability time scales, and the spatial scale of information we are getting. So let's go now quickly show some applications. Okay. I'll start to show a simple approach, a simple extreme sea level approach that takes into account the mean sea level uncertainty. Okay, this is an example. I took the San Francisco tide gauge. It has a long hourly total elevation record, and I chosen the maxima values, and here you can see the return level plot. Circles are the only maxima values, and I fit a stationary extreme value model. So, guess now that coastal engineering needs to design a seawall at San Francisco, and guess that the mean sea level experts has consensus about what is going to be the mean sea level rise in the future there. So the mean sea level experts say to the coastal engineering, okay, you are going to have an increase of 38 centimeters because you have a trend of something like about 1.4 millimeters per year. So this is going to be, this is the common behavior people do. This is going to be the extreme values, the return level values in 2100. Okay, it's just a linear assumption that if the mean sea level rise increase, the extreme sea levels are going to increase in the same way. But we can obtain this result not only by doing a simple sum of this theoretical line, but also by applying the joint probability method. You should know the joint probability method applies for tight and surge, but here I have applied the joint probability method by assuming the extreme sea level total elevation and the mean sea level rise function. So now, guess that we are not sure that the trend is going to be 1.4 millimeters per year. So maybe we have not one value, we have a distribution of the mean sea level rise. We know the uncertainty of that. If we assume, for example, that we have a standard deviation of this trend of 0.1 centimeters, this is the result. So you can see that we take into account the uncertainty of the mean sea level rise, our estimation of the return levels are higher. For example, the engineer can have for the 100 return level, today we have something like 4.4 meters, and in the future we can have more than 4.8 meters. Okay, let's go to see a different example. This is an example of how we can study the influence of different climate variability time scales. To do that, I have modeled a time-dependent GEV distribution. So I allow the location, scale, and Z parameter of the distribution that modify the distribution on the way you can see in the pictures to be time dependent. And I have applied this model to two long tight gauge records, the San Francisco tight gauge record and the New York tight gauge record. And here I'm showing on the right the results for the San Francisco tight gauge record. The bottom panel shows here the final behavior of this scale parameter. We have seasonality and trend. And here you can see the final behavior of the location parameter. This is a combination of different factors: a trend, a nodal astronomical modulation, seasonality, the influence of El Niño, an extra trend on trends, and at the end we can obtain the 100 return level estimation throughout the time. We can do the same for the Newlin tight case, and we have got a very different behavior. We have got that here the dominant factors are astronomical modulations. There is no significant El Niño influence here. And we have, for example, if we look at the location parameter, here we have a trend, a seasonal pattern, a nodal modulation, also perihelion modulation. Here, because we have not a climate index or an internal variability significant, we can obtain the 100 return level, and we can extrapolate this model to the future. We have applied the same extreme value model to several tight gauge records in Europe, and here I'm showing the result about a research on the influence of the astronomical modulations on this extreme sea level behavior. And here you can see that we have obtained for the tight gauge record in the North Sea a clear influence of the nodal cycle. If we go to the open Atlantic coast tight gauge, we have got nodal plus perihelion influence. And if we go to the Mediterranean Sea, the Venice tight gauge record, we have found only the perihelion influence to be significant. So we have obtained here, we can obtain from this result some kind of regional description. So let's go now to show a different regional analysis by using not only tight gauge records but also model outputs. To do that, I have reconstruct 60 years of hourly flat levels nearshore. So here I'm not only including what is currently named still water level, I have also some the run-up. So this is the combination of the run-up and tight storm surge, regional mean sea levels and the reference level. So we have reconstruct this 60 year of hourly time series for all the tiny red dots that maybe you can see here along the whole Spanish coast. So here we have Mediterranean region, we have open Atlantic region, and we have Canary Islands in a very in a lower latitude location. From this model, from this data, I have applied a Pareto-Poisson model that it takes into account frequency and magnitude for the extreme sea levels, and I have allowed the model to have trends, linear trends. We can estimate the 50-year return flat level, and here is the result. So you can see we have a clear spatial variability at regional scale. We have lower values along the Mediterranean coast, higher values on the north shores of Spain, and we have also a clear variability in Canary Islands with higher values in the northwestern coast of the Canary Islands. But because we have allowed a trend in this model, we can estimate, okay, we have 60 years of historical reconstruction, so we can assume now we are going to extrapolate to the future, to the next 30 years. And we can estimate the increase or decrease that our trends provide. And this is the result for the horizon year 2040. And here you can see the increase that we have obtained for this year with respect to the estimated 50-year return level today. So we have obtained not very big trends along the Mediterranean coast. Higher trends are in the North Shore and also in the south and east coast of Canary Islands. So a different example, if we go to a global tight gauge data set, this is a result when we try to analyze the influence of ENSO phenomena on the extreme values from all these tight gauge records. You can see we have obtained a clear influence of ENSO phenomena, positive in the Eastern Pacific Ocean and negative in the Western Pacific Ocean. But also we have a weaker but a relevant influence in the US East Coast. We can apply this model also to see if the increase on extreme sea level events are due to the mean sea level behavior, or there is any additional physical process that is changing our extreme sea level events. On the top you can see the trend estimated on the 50-year return level by using the total elevation records. You can see here a general increase. This increase is so relevant in the US coast, Europe, and all these regions. But if we remove the annual medians, that is like we are trying to remove the behavior of the mean sea level rise, we have got, applying the same methods, we have got the results. Black dots mean not significant trends. So here we have a lot of not significant trends. So it means that most of the general increase on extreme sea level events is due to the mean sea level rise. But of course, here we have still red areas, and the most relevant red regions are Europe and maybe China and India. That's all. Just to conclude, say that main critical factors for an adequate analysis of extreme sea level change are to be able to have as long as possible records and with the better quality as possible, that we need to choose the extreme model depending on the goal we want to achieve, that understanding shorter time scales help for a good evaluation of long-term trends. The time-dependent extreme analysis is valid for different sea level variables and data sets. That these time-dependent, these non-stationary extreme value models help us to obtain climate information. Thank you very much.